Hello students, in previous class I have explained you about the Bohr's theory for hydrogen atom. Let's see about the other atoms. So Bohr's theory is particularly applicable for hydrogen atom, but it can be applicable for the hydrogen-like species. Hydrogen-like species means the species which contain only one electron, like He plus, Li2 plus, Be3 plus, and so on. So energy for the hydrogen-like species is minus 2.18 into 10 raised to power minus 18 Z square divided by N square joule. Alright, here Z is the atomic number. And R which is radius is equals to 52.9 n square divided by z. Similarly, here z is z is atomic number and n is principal quantum number. The unit of radius is in picometers. And here this is A naught, which value is 52.9 picometers. So if we want to calculate delta E means difference in energy, that means E final minus E initial. Alright, we get this relationship. Here, Ni is represented for the initial energy and Nf is represented for the final orbital. Alright, similarly, we can calculate the frequency as we know that delta E is equals to h nu. If we want to calculate mu, then we have to divide delta E by h. So divide this term with the h, that is Planck's constant, we get this term, and this is the frequency. Alright, if we want to calculate wave number, we know that wave number is equals to 1 by lambda, and frequency is equals to c by lambda. So to calculate 1 by lambda, we have to divide frequency with the c, that is 1 by lambda is equals to wave number. So frequency divided by light of speed is the wave number. So overall equation is this, and this represents the wave number in terms of principal quantum numbers. Let's see what are the limitations of Bohr's model. So this Bohr model does not explain for the species which contain two electrons. Alright, it is applicable up to the hydrogen or hydrogen-like species which contain only one electron. It doesn't explain the Zeeman effect or the Stark effect. It couldn't explain the chemical bonding, and it actually ignores the dual behavior of matter, which is also contradicts the Heisenberg uncertainty principle. Let's see what is the Heisenberg uncertainty principle. Heisenberg uncertainty principle is basically delta x into delta px is equal to or greater than h by 4 pi. That means, according to Heisenberg, it is impossible to determine simultaneously the exact position and the exact momentum of an electron. Alright, it is so difficult to calculate exact position. We may calculate either the exact position or the exact momentum, but it is impossible to determine them simultaneously. Alright, so this is a basic relationship for the Heisenberg uncertainty principle. Here P is linear momentum, and we know that P is equals to mv. If we talk about the change in linear momentum, mass is the constant term. The term change is the velocity. So delta x into delta v is equals to or greater than h by 4 pi m. Alright, if we want to know the relationship between delta x and delta vx, we can say delta x is inversely proportional to the velocity. Alright, but Heisenberg uncertainty principle is just only for the microscopic particles. So let's see the significance of uncertainty principle. It helps in to determine the trajectory of the electron. It is applicable for the microscopic object and neglect the macroscopic object. Alright, like here we calculate for the milligram size. Here the delta V and the delta X is equals to 10 raised to power minus 4, which is impossible. Even the light speed, which can be traveled so fast, has a speed of 10 raised to power minus 8. Alright, so this is the significance, or we can say this is particularly drawback, that it is applicable up to the microscopic object, not applicable for the macroscopic object. Alright, thank you.